Section 1.5, complex numbers. Note that if I tried to solve the equation x squared plus 1 equals 0, then x squared will equal -1. But that means by the square root property that x is equal to plus or minus the square root of -1. So what in the world does the square root of -1 mean? Since we want to be able to solve, hopefully, every quadratic equation with real coefficients, then we have a problem if we're not able to solve this simple quadratic equation, monoquadratic equation with a natural number in it. So we're going to somehow try to make sense of the square root of -1. So first what I'll do is I will define what we call complex numbers, which are an extension of our idea of a number, so that we will be able to solve any quadratic. Okay, so complex numbers. We'll denote the set of complex numbers by the letter C. It'll just be the Cartesian product of the real numbers with itself. And we'll define an algebra on these, some algebraic operations on these sets of ordered pairs. So if I have the ordered pair AB and I want to add to it an ordered pair CD, then this will be the ordered pair A plus C, comma, B plus D. If I want to define the operation of multiplication, then the product of the ordered pair AB with the ordered pair CD is just the ordered pair A times C minus BD, comma, AD plus BC. We have the additive identity, which is just the ordered pair 0, 0. The additive inverse of the ordered pair AB is the ordered pair -A, -B. The multiplicative identity is just the ordered pair 1, 0. The multiplicative inverse of the ordered pair AB, not equaling the origin 0, 0, is the ordered pair A over A squared plus B, comma, -B over A squared plus B. I will use the following notation. I'll let I equal the ordered pair 0, 1. And so the ordered pair AB will be denoted by A plus BI. Note the following, that I squared, remember I is just 0, 1, times 0, 1, so that's I squared, is just, by definition, 0 times 0 minus 1 times 1, comma, 0 times 1 minus, plus 1 times 0. And so I get a -1, comma 0. But in this notation here, this is just a -1 plus 0i, or -1. So I have that I squared is -1. And so I've now made sense of the concept of what's the square root of -1. Well, it's just the ordered pair 0, 1. And so I'll define the set of complex numbers. So now that I've made sense of this, I can now use the fact that I squared equals -1. So I'll now define the set of complex numbers as a set of all numbers of the form A plus BI, where A is a real number and B is a real number, where we have that I squared is -1. Usually, we denote the complex number a plus bi with the letter z. We call a the real part is z, and we denote it by re of z, that's a. And we call b the imaginary part is z. Notice that both a and b are real numbers. I should probably have said that. So note that each of these are real numbers. So even the imaginary part is a real number. Okay. Note the following. I to the power 0 is 1. Any non-zero quantity to the power 0 is 1. I to the 1 is just I. I squared, well, I said it was -1. I cubed is just I times I squared, which is -1. Well, I times -1 is just -I. I to the 4th, well, that's I squared squared. I squared is -1. -1 squared is 1. I to the 5th is I times I to the 4th. So I times 1 is just I. I to the 6th is just I times I to the 5th. I times I is just -1. I to the 7th is I to the 6th times I. I to the 6th is -1 times I is -I. I to the 7, I to the 8 is I squared to the 4th. -1 to the 4th, it's just 1. And so, as you notice, we have a pattern here. So I to the 9th is I to the 10th, -1, I to the 11, -I to the 12, 1, I to the 13, I to the 14, -1, I to the 15, I, etc. So let me write that down. But in order to do that, let me give you the concept of a modulo. And so the concept of a modular arithmetic. And so let m and n be natural numbers. Then m modulo n, denoted by mod. This will denote the remainder of m divided by n. And so if you divide two natural numbers, you'll get some natural number plus a remainder over your divisor. And so we just take the remainder part. And so the important thing, so say you have 5 divided by 3 is 1 with a remainder of 2. So 5 mod 3 is 2. It's just the remainder. So we're only looking at that remainder part. So I to the n is equal to 1 if n mod 4 is 0, I if n mod 4 is 1, -I if n mod 4 is 2, -I if n mod 4 is 3. So you notice that if you divide each of these exponents by 4, then it looks like one of these. And so this is the pattern. The complex conjugate. So the complex conjugate of the complex number z equaling a plus bi is just denoted by a bar over the complex number, and it's just the real part minus the imaginary part times I. So it's a minus bi. The modulus of z, the norm of z, is just the square root of z times its complex conjugate. It's the square root of a squared plus b squared. And so it's the square root of the real part squared plus the imaginary part squared. So let's do some examples. And so when dealing with complex numbers, we just deal with them the same way that we've dealt with the numbers, real numbers. We just use the fact that I squared is -1. And that's all we really need. So let's do on page 138, problem number 12, simplify the imaginary numbers. And so I want to simplify 7 times rad -48. Just like before, I want to write this as the largest perfect square factor times, well, the other factor. And so let's write -48 is -16 times 3. And so the square root of -16, well, is 4i rad 3. And so 7 times 4 is 28 I rad 3. Note, just as always, best to write the number first, followed by any constant that's written as a symbol, times variables, and then lastly, the roots, the radicals. So I can simplify this as 28i rad 3. Let me do problem number 18. Find the values of x and y such that, well, x plus 5i is equal to y plus yi. I'm assuming here that these are real. So I'll just make the assumption that x and y are real. To solve this, then the real parts must be equal and the imaginary parts must be equal. So from this, I get that y must equal -5. But since from the first equation here, I have that x is equal to y, x must equal -5. And that is my answer. Okay, so let's do the next one. Let's do problem number 26. Move it up. Perform all operations. Give all answers in the standard form, a plus bi. So in the a plus bi form. So problem 26, 5 plus rad -64 minus 23i minus 32. First, let me simplify the square root of -64. Well, the square root of 64 is 8, and the square root of a negative number is I. Next, let's get rid of the parentheses. So let's change all the signs inside the parentheses. So this is equal to 5 plus 8i minus 23i plus 32. Now let's combine like terms. 5 plus 32 is 37. 8i minus 23i is a negative 15i. And that is in the form we wanted. So notice that we treat these just exactly the same way we did in previous sections. We treat this I here as sort of a indeterminate, a variable. So, if these were like apples or something, it would work the same way. So the algebra that I introduced before just said, well, treat everything the same way you've done it before. Okay, let me do problem number 33. And so to do this, let me just multiply first. So let's use the distributive property. 2 times 3 is 6. 2 times 5i is 10i. 3i times 3 is 9i. 3 times 5 is 15. I squared. But notice that I squared is negative 1. And so this is equal to 6 plus, well, 10i plus 9i, combined like terms is just 19i. And 15 times negative 1 is a negative 15. And so this is equal to negative 9, combining 6 minus 15, negative 9, plus 19i. And that is in standard form. Okay. So you notice that we've done nothing different. We just simplified the same way we've always simplified. Let me do problem number 50. Well, we actually gave a fairly strange definition above for the idea of what it means to be to divide. But what we'll see is that it's actually a very easy concept once we use this notation. And so what I want to do here is I want to write this in the form a plus bi. So I don't want an I in the denominator. So what I'll do is I'll multiply and divide by the complex conjugate of the denominator. And this was, if you remember, when we were trying to rationalize numerators or denominators with radicals, we said that, we were multiplying by a conjugate. The reason we called it the conjugate is because, well, this is the complex conjugate. So let's multiply. And so let's multiply 3 and negative I. So this is going to equal 3 minus 3i minus I plus negative times negative is a positive I squared. Now notice in the denominator, this is the product of the sum and difference of two terms. And so this is the difference of their squares. And so I can simplify this. Recall I squared is negative 1. And so this is equal to 3 minus 3i minus 1i is minus 4i. I squared is negative 1. I squared is negative 1, so this 1 minus I squared becomes a 1 plus 1. 3 minus 1 is 2, minus 4i, all divided by 2. Let me factor out a 2 from the numerator. So we get a 1 minus 2i, all divided by 2. The 2's cancel. And so you get 1 minus 2i. And that is your answer. Let me do problem number 59. And let me do it two different ways, I guess. Or I'll do it this way. So I to the 38. So it says here, simplify each expression. And so in problem 59, I want to simplify I to the power 38. So first, what I want to do is write this as the sum of two numbers, one of which is a factor of 9, the largest factor of 9. And so the largest, if you divide 38 by 4, it's the quotient. And so the quotient would be 9. And so this is equal to I to the 4th to the 9th times, well, I squared by the properties of exponents. I to the 4th, well, let me see. I squared is -1. So -1 squared is 1. So I to the 4th is 1. And I squared is, well, I squared. So this is just equal to I squared. But I know that I squared is -1. So my answer is -1. Okay, so what we see here, and this is what we noted from before, is that all I really needed to do is to divide 38 by 4 and look at its remainder. Well, if I divide 38 by 4, I get a 36. Well, I get a 9 with a remainder of 2. And so I to the 38 is the same as I squared, which is -1. And so let's divide 201 by 4. And so I'll get 201 divided by 4. Well, that's 50 with the remainder 1. So this is I to the 1st. And so this is just equal to I. Okay. Let me do problem number 74. Write without absolute value symbols. And so let's do that. Actually, I can move this up by 1 maybe. Yeah, it'll be a little tight, but not too bad. So write without absolute value symbols. The absolute value of 12 plus I. So let's find the modulus of this complex number. Well, if you recall, this is just the square root of 5 plus 12i times 5 minus 12i. It is just the square root of 5 squared plus 12 squared. Or you can think of it as, and maybe I'll do this. This is the product of the sum and difference of two terms. So it's the difference of their squares. But I squared is -1. And so this is just equal to the square root of a squared plus b squared, which is what we had before. And so this is square root of 25 plus 144, square root of 169 is 13. And so my answer is 13. So that's the modulus of my number, the absolute value of 5 plus 12i. Let me do problem number 90. I certainly don't have enough room. Let me put this down a little bit. One second, let's get some space. Okay, so solve each quadratic equation using the square root property. X squared equals negative 81. So by the square root property, x is equal to plus or minus the square root of negative 81 The square root of negative 81 is just 9i. And so I have two solutions. They're both imaginary numbers, plus or minus 9i. Let me do problem 116. Solve the following quadratic equation by using the quadratic formula. Simplify the solutions and write them in the form, the standard form, a plus bi. And so I have here on problem 116, x squared minus 3z is equal to negative 8. And so z, I have to write this in exactly the same form that we had derived the quadratic formula. So I have to have that this is equal to 0. So let's add 8 to both sides of my equation. So now that I've written it in this form, I can use the fact that z is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's figure out what z is. So z is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So z is equal to 3 plus or minus the square root of 9 minus 32, all divided by 2. Well, 9 minus 32 is negative 21. The square root of a negative number is just I times the square root of that number. So it's 3 plus or minus I rad 21. I really can't do anything with rad 21. And this is my answer. However, technically they wanted it in the form a plus bi, So I should write it in the following form. So I'll just say that the answer, but they want it in the form A, so divide the first term by 2 plus or minus the square root of 21 over 2 I. So this is the form they wanted, the standard form. But as I say, the previous form is perfectly fine. Oh, and that finishes off section 1.5.